welcome back. This is A Level Computer Science 9618, Chapter 4, Part 2, which is Assembly Language. And welcome to our Parts YouTube channel. Okay, so inside the assembly language, whenever we try to execute the instruction in assembly language, it consists of two parts, the opcode and the operand. The opcode is what do we need to do. It is the operation, right? And the operand is it could be an actual data or address. Okay. So for each machine code instruction, there is an equivalent assembly language instruction which comprise a mnemonic symbolic abbreviation for the opcode. This is the mnemonic. Okay, this is the mnemonic. This is the opcode. And the character representation for the operand. Okay, we can we the il, when for the operand it could be an actual address, you can even call it a data, or it could be a variable that has stored that address. Okay, so whenever we try to use these variables for those when we try to use meaningful variables for these addresses, we call them symbolic address. But whenever we try to use numbers, right, 230, which is the address, right, so it would be known as absolute addressing. Okay, so let's see right here, this is the opcode. Okay, this is the operand. The operand in the operand, these are variables, and these variable have stored the address. Like the first will come here, first has stored these are the variables, and it has stored these addresses, right? Like LDD first. What is LDD? Okay, we'll discuss this later. For now, this is the opcode. It tells us the operation, that what do we need to do with these addresses or data. Okay, so let's get down here. Okay, if a program has been written in assembly language, it has to be translated into machine code before it can be executed by the processor. The translation program is called an assembler. Like for example, if we are using a compiling a Java, if we are using any high level languages and we need to compile that high level language, we use a compiler or interpreter. But for an assembly language, whenever we try to write the code in assembly language, we try to use the assembler. Okay, so an assembler is used to allow a programmer to include some special features in an assembly language program. Example of these are, we can add comments, we can have symbolic names for constant symbolic names like these are symbolic names. We have variables that have stored the address. We have meaningful variables that could represent a meaningful uh, you know it gives obviously that's why we use the variable, right? We try to make sure to that we give meaningful variables to make us understand that what we are doing right here. Okay, so we got symbolic name for constant, the first three to assist the programmer. Okay, so we got label for addresses, same thing for now, symbolic names. Okay, symbolic addressing, it's this is telling us that we use symbolic addressing. Labels for addresses. Okay, symbolic names for constants, symbolic names for constants, we use symbolic names. These are at some point symbolic, right? These three letters are symbolic. ADD, which means adding, STR, which means storing, END, which means and, LDD is LDD. We'll see this. What is the meaning of that? Okay. Then we have macros. Macros is a function. Subroutine is a built-in function. Directive and system calls. Macro is a group of instruction given a name, a group of instructions that needs to be executed several times within the same program. The statement are written once and called using the name whenever they need to be executed. Okay, the directive, an instruction that direct the assembler to do something. A directive is not a program instruction, it is information for the assembler, how the assembler should construct the final executable machine code. So that's why we use directive, right? That's what directive is for, giving a direction. Okay, giving an instruction, but it's not a program, it's just the information, it's just information for the assembler, that how the assembler should construct the final executable machine code. Okay, System calls is function provided by the kernel OS to enter into kernel mode to access a resource. You will learn about this in computer P3. Okay, moving on. Then we have two pass assembler. In one pass, okay, whenever the assembly language is executed, whenever we try to so whenever we try to execute before it can be executed by the translation program is called assembler. The assembler try to translate that, so it is consists of two stages. The first pass assembler and two pass assembler. In first pass assembler, the assembler adds entries to a symbol table. In one pass assembler, the assembler add entries to a symbol table. Okay, symbol table. So what's happening here? For example, we have this instruction. We're going to make a symbol table. Okay, so what would be included in this is a symbol. This is the symbol table. We try to put all the labels in one side, and then we put the equivalent addresses of that label on the other side. So this is the label start, and this is the value 100. Okay, first this is start, and the value of this is 100. For the first is 106, second is 107, and so on. So this is absolute addressing, and this is a symbolic table. So this is the job of first pass assembler. Okay, the assembler scans the assembly language instruction in sequence. When it meets a symbolic address, check to see if it already in symbol table. If not, it add it to the symbol table in the symbolic address column. If it is already in symbol table, check if its absolute address is known. If the absolute address is known, it is entered in the appropriate cell. If the absolute address is not known, it leaves as unknown. If we know the absolute address, then fine, we put it there. If we do not know, then we mark it as unknown. Okay. Any directive acted upon, data items are converted into their binary equivalent. Okay. So that's the job of first pass assembler. Now we are coming to second pass. In second pass assembler, the instruction table is needed when building up the executable file. Instruction table, the symbol table, right? We need that. Any symbolic address is replaced by an absolute addressing. Forward reference are resolved. Okay. After making the table, then we try to use this table, and then we replace those label with addresses, and then we try to execute the code. So this is the job of two pass assembler. Okay, two pass assembler needs to scan the source program twice, so they can replace labels in the assembly program with memory address in the machine code program. And there you go. This is how it is done. Okay, so we have understood about the instruction that consists of two-part opcode operand. We understood that we use meaningful labels for understanding it and making code in assembly language. And then how the assembler works, it works in two parts. First pass assembler, it tries to try to make a symbolic table, and then in two pass assembler, it tries to replace label with addresses and then execute the code. Okay, we got the special features inside when writing in assembly language. Okay, so these features, and we are done with it. 80%. Let's move on. Okay, now we need to understand the relationship between assembly language and machine code stages of the assembly language. Okay, we have already done this. Set of instruction are grouped. Okay, this is the real deal. Here it is. These are the instructions. This is the opcode. This is the opcode that we need to understand how each one of them are working, right? For example, LDX is for this, LDM is for this, LDD address. Okay, LDMN, this is the decimal. Whenever we have these kind of symbol, we represent any number. Whenever we have this kind of symbol, we represent binary number, and in this way we represent hexadecimal. Okay, ACC is the accumulator, IX is index register address, which can be an absolute or symbolic address. Okay. For example, LDM, this immediate addressing, load the number n to accumulator. LDD direct addressing. Load the content of the location at the given address to ACC. Okay, this is direct. We are taking the content of that location of the given address to accumulator. We are storing the value by getting the content of that given address. Okay, this is direct. Okay, indirect means the address to be used is at the given address. Load the okay. Indirect addressing. The address to be used is at the given address. Load the content of the second. Okay. The address to be used is at the given address. The address to be used is at the given address. So it is the address of the address. The indirect addressing means address of the address. Address of the address, and then it says load the content of the second address to accumulator. So this is indirect. Index means from address plus the content of the index register. Copy the content of this calculate address to accumulator. Immediate addressing, load the number n to this. Okay, move the content of the accumulator to into the given at register. Store the content of accumulator at the given address. Add the content of the given address to the accumulator. Add the number n to the accumulator. Subtract, increment, decrement, jump, compare. Indirect, which means the address to be used is at the given address. Compare the content of the accumulator with the content of this second. Okay. It says the address to be used at the given address of the address, and then we try to compare with the content of the accumulator and the content of the second address. JPE, following a compare instruction. JPN, following a compare instruction. Okay, jump to address if it is true, jump to address if it is false. In, which means input any key value from the user. Output, which means output to the screen at the character whose ASCII value is stored in the accumulator. And, which means and the program, and return control to the operating system. This is the assembly language. We have the opcode and we have the operand. Okay, so this is a part of data movement. We are moving the data to there, from here to here, like storing, moving. Okay, loading any value in the index register, loading LDX, which means making an address and using the address to the taking the content, uh, copying the content and storing in accumulator. Also storing in accumulator data movement. Okay, taking out the content from the given address and storing in accumulator. Then we have the arithmetic operation where we are doing addition, subtraction, increment, decrement. Then we have comparison and jump where we try to compare uh, the content of a accumulator with the content of the address. Compare. We have we also comparing here. There's also comparing. We just try to jump to that particular address. Okay, so this is comparison and jump. Input and input giving input from the user, outputting showing the output to the screen. Whatever it is found in the accumulator, it would be shown to the screen. Okay, and which means end the program. So this is assembly language. So set of instruction are group. So these were the 5 groups that I've just showed you. When an instruction requires a value to be loaded into a register, there are different ways of identifying the value. Okay, when an instruction requires a value to be loaded into a register, there are different ways of identifying the value. Okay. Okay, so there are different way of identifying the values. Okay, these are the different ways. Okay, different modes of addressing. Immediate, the operand is the value to be used. Immediate, right here, immediate. Load the number into accumulator. This is completely directly. Okay, immediate direct, the operand is the address of the value to be used. Indirect, the operand is the address of the value to be used. Index, the operand plus content of the index register is the address of the value to be used. Related, the operand is the offset from the current address of the value to be used is stored. It might be connected to a program counter, right? Taking the value from the program counter, and I mean having its own address, his own operand. For example, uh, Like for example, if the register have stored 20, and then we're taking the value from the PC, which is 200, we add them up it from the address, and then we use the address to get the content, and the content, after getting the content, we are storing in the accumulator. So this is what it means for now. Since it has not been used, but still don't worry about it. It must be connected to the program counter. Okay, taking in from the program counter as well, and having itself the address as well, adding it up, it forms the address, and then it goes to the memory location. It gets the content, then it's stored into the accumulator. All right, let's move on. So you all know this, right? Fine. Okay, now let's do the questions. So we have the instructions. This is the ASCII code table. These are the instructions for us, for our understanding. It would help us. This is the question. Complete the trace table for the given, okay, for the given assembly language program. Okay. So right now the first address is instruction address 70, and here you go. This is 70 LDX 200. LDX, what is LDX? LDX means this is index address from address plus the content of the index register. Okay. So the content of the index register is 0. So it would be 200. Copy the content of the calculated address to accumulator. Okay, we got the address. So the address is 200, and inside 200 it is 130. And so copy the content of the character address to accumulator. So we're going to add store 130 into the accumulator, and there you go, 130. Now we got 71. Okay. Out means output to the screen. Output to the screen, the character whose ASCII value is stored in the accumulator. Okay, this is the ASCII code, and we got 130. So this would be the output. The star is the output. So this is the output. Okay. Now let's see 72. So now it says store 203. STO means store the content of the accumulator at the given address. Okay, so accumulator have 130, and it said store 203. 203, storing it here. So it would be what was the content? The content is 130. Okay, so 203. 203, which means it was a 72. 203, so it was store 130. Okay, 73. LDD 204. LDD direct addressing, load the content of the location at the given address to accumulator. Okay, this is direct, it's much easier. LDD 204 is here. This is 0. We need to add 0 in the accumulator. There you go. 74. What is 74? Increment accumulator to 1. So we're going to increment it. It's going to be 1, then 75. Okay, let's see here. 75. It says store 204. Okay, store 204. What does that mean? Okay, content of accumulator at the given address 204. So we're going to store the value 1 in here. 76. Increment ix. Incrementing ix, and the ix is here. Okay, 77. LDX 200, and yeah, so 200 plus the content of index register, so 201, and using that, Okay, 201. So this is 133 right here. Now storing this in the accumulator. So 133, 78 compare 203. Okay. So CMP, what is CMP? Compare the content of the accumulator with the content of address. So compare, okay, content of accumulator. So 203, this is 203, which is 130. Okay, so it was 130. Comparing this to the value of the accumulator. All right, and after comparing it even in here, then GPN 79. So I just compared and it is false, it's not same. 79 GPN 81 GPN volume compare, so you jump to it if the compare was false. Okay, jump to this edge if the compare was false and it is false. They are both different. 130 and 133, they are not equal. So we're going to jump to the address if the condition is false. Jump to 81. We have jumped to 81. Okay, LTT. So we have jumped to 81, which is going to be 81. How much it is left? So long. Wow. LTT 204. This is direct addressing. Okay, 204 0. So we're going to put 0. We're going to put 0, I think. Wait. 204. Okay, so 204. This is 204 and it got the value 1. First of all, it says, you know, load the content of the given location address to accumulator. So load the content of the given load the content of the location at the given address to accumulator. So this is 204 and the value must be 1. Okay, since it's in here it is 1. So load the content of the given address to accumulator. So accumulate the value for that for the accumulator would be 1. Here you go. 82 CMP 205. Also we're going to compare CMP. Comparing it, after comparing it, it's going to be 83. JPN 74. And JPN means if the compare false, go to this address. And so CMP 205, which is 2. Comparing this to the accumulator and it is false. So we're going to jump to this address 74 because it is false, obviously. So going back to here, increment accumulator. Okay, the value for the accumulator was 1 and now we're going to make it to 2. So 74 and it's going to be 2. Okay, now 75. This is so long though, very very long. 75 store 204, store the content of the accumulator given address. Okay, so the accumulator have 2 and store in this address 204. Okay, so it's going to be, now it's going to be 2. Okay, which means it's going to be right here 75 and it's going to be stored here 2. 76 says increment ix, incrementing it. So it's going to be 2 as well. Then 77 we have LDX 200 plus the content of the index register, which is 2, 200 plus 2, 202, and we got 130, and load this to accumulator. So 130, this is going to be 130 again. Okay. Okay. So 130, 130, 77, 78. Doing compare again, 203. CMP means compare the corner of the equator. Okay. So 203 is 0. No, it is 130. It is equal. And since we are doing comparison, 78, it is comparison. 78 is comparison. 79. Okay, 79 and 80. Obviously it is true. So 80. Look, guys, this is 203, right? This got the value 130, 130. It compared, after compared, if it was false, it would go to that particular address, but since it is not false, it is true, we move on and come to address 80, which is out, and out means output to the screen by using the value of the accumulator. So it is 130, and since it is 130, which means we're going to put star. Okay, 130, and it's going to be star. And that's it. This is done. The whole thing is done. Okay. Wow. So this is the address. This is how you do addressing. This is how the instruction works, right? I hope you understand what is the assembly language. This is the opcode, this is the operand, you can call it, you can use an address, these are address, but you can also put labels, meaningful variables to make it more meaningful, make it more understandable, right? Let's go on. Now we have moved to bit manipulation. Bit manipulation comes in when we are trying to doing monitoring and control, right? We got sensors, we got, the sensor is giving us a flag, whether any particular condition is true or false, giving an alarm if anything goes wrong. So all of these kind of stuff comes in bit manipulation. We use bit manipulation, right? It used in sensors and monitoring. So in monitoring control, each bit in a register or memory location can be used as a flag and would need to be tested, set, or cleared separately. Okay, so whenever we try to do, let's come here for now. Okay, bit manipulation, binary shifts. These are the binary shifts: logical shift, arithmetic shift, cyclic shift. Logical shift means bits shifted out of the register are replaced with zeros. For example, if we are going to left or right, it would be replaced with zero. For example, it is going left, right? So one is gone, zero, and another one is gone. So these would be left, and there you go. Similar thing if we go to the right side. So bits shifted out of the register are replaced with zeros. Then we got arithmetic shift. Okay, so arithmetic shift is used for multiplication or division by power of 2. Okay, the sign of the number is preserved, which means the sign does not change whenever we try to shift this to, yeah, the sign does not change. Okay, it is preserved. That's why we use that's the meaning of arithmetic shift. When shifting right with an arithmetic right shift, the least significant bit is lost, but if we go to the left, then the most significant bit is copied. For example, in here, if we go to the left, then 0 will come here, and it will go there, and 1 will be lost, right? It will be deleted, so it will come like here, and zeros add up. But if we go to the right, this will be copied down to here, and it goes from here, 1 is here, then like that. So going to the right, the most significant bit is copied down. Going to the left, it will be deleted. Okay, yes. Similarly, for example, if we are going to the right, so it will go right, it will be 1 0 1, and the most significant bigger, okay, if we are going to the Okay, okay. If we are going to the left, it will be going to the left, 0 will be added up, it will come down like this. If we go to the right, then the most significant bit is copied down here, right? So going to the right, the most significant is copied down. Going to the right, the most significant bit copied down. Like for example, it goes here, one comes, then goes here, one comes, goes here, one comes. So all of them are one. Similarly, okay. Similarly, depend whether it's 1 or 0. If it is 0, then 0 will be copied down. If we go to the right side, it went to the right side two times, so 0 will be copied down. Okay. For example, if we have the value of 123 and if we just multiply by 2, then the in bit form it will be to it will go to left. It will go to left. If we try to do multiplication, if we try to do division, it will go to right, the bit, you know the bit shifting. Okay, so that's the meaning. Can be used for multiplication or division by power of 2, 2 or 2 of power 3, 2 of power 1, 2 of power 2. Okay, this is arithmetic shift. Then we got cyclic shift. It's very easy. No bits are lost during a shift. If whether we go from left or right, it's a complete loop. It doesn't The bits doesn't are not lost. Okay. If we go left side, one comes there and it comes back. Zero comes there and it comes back. Okay. So one comes back. Then we got zero comes back. Then and one also come back. So there you go. 101, 101, 0 is here and 0 is here. Okay, so this is cyclic shift. And we got this bit masking. Bit masking would be used whenever we try to use to check if the bit has been set. Obviously it is used for sensors and monitoring control. Don't worry, we will get these kind of question. Okay, used to check if the bit has been set, we use AND. Used to set the bit, we use OR. Used to clear a bit that has been set, which we use XOR. Okay, so it's very simple. It's same thing like we have done is in logic gates, right? And which means multiplication, OR means plus, and XOR is a complete different scenario, right? So we will get this table, right? And we can have in decimal, in binary, or in hexa, bitwise and operation of the content ACT with the operand. Okay, so we are doing AND operation with the content of the accumulator with the operand, with the given operand. Okay, we can also we could also be given with the address, content of the add with the content of the address. Same here, LLS shifted logically. Okay, this is left shifting, this is right shifting. Placed to the left, zeros are introduced on the right hand, zeros are introduced on the left hand. We got the opcode, labels and instruction. Okay, we try to label it. Labels and instruction. Data gives a symbolic address labeled to the memory location with the content data. This is a different thing. Okay, so yeah, this is the end of this chapter, which is assembly language. Okay, so thank you so much for watching. This is the end of this chapter, chapter 4, and I think I'm going to move on to P2, I guess, programming language. Okay, so it's going to be really, really fun if I'm going there because I've already studied a lot, I've done a lot of coding, and I think I'm going to make a huge course for this programming P2. Okay, so it's going to be the course would be covered in Visual Basic Studio with pseudocode and some extra, you know, I'm going to make a video when I'm doing a code, and also I'm going to write it down as when doing same thing. Then I'm going to compile it and give and prepare this course, this P2 programming completely in one video. Thank you so much for watching. Hope you have a good day and enjoy, and good luck for your exam. Thank you.